going to kick off with our special guest, Philipp R from Chicago, who's, you've heard, those of you at the dinner last night, about the fantastic, well, we saw the documentary last night at the dinner, which was quite fantastic. So Philipp is associated with the University of Chicago and also with the Field Museum in Chicago. So could we please welcome Philipp to the stage.
Thank you very much, Grim. Thank you for inviting me to speak here. I'd like to thank Kai Bell for organizing and the Murchison Historical Society for organizing this, and Graham Beck, and also Paul Waring, and Lynn Waring, who've been wonderful hosts to me this week. And it is so exciting to be here in Murchison. Murchison is my favorite meteorite. It's the meteorite I started working on when I started working in Cosmochemistry in 2002. And many papers I worked on are on components of Murchison, presolar materials, and I'll talk about this now. And it's unbelievable just coming in to the town of Murchison, seeing the sign Murchison, seeing the service station Murchison. I took pictures of everything, bring it back to Chicago. And it's really exciting to be here during the 50th anniversary of the fall. And I'd like to thank Murchison and the citizens of Murchison to have made the samples available to the scientific community. Without that, our knowledge of the early solar system would be not as rich as it is today. And these are some of the samples that were collected and laid out in the post office. Another beautiful picture of one of the large fragments that were collected. And this is one of the large fragments is currently in Chicago in public display at the beginning of our gallery where we talk about the origin of life. And this is the first specimen that's there on display, and it's visited every year. The museum is visited by over 1 million people, and they see Murchison at the beginning of that exhibit. The biggest piece I think that we have is 6.5 kilos, and I think that's the biggest piece that was recovered, to my knowledge, but correct me if I'm wrong. There might be bigger pieces around that we don't know of, and thanks to the generosity of the people of Murchison who made this available to science and to donors from the Chicago area who actually purchased this and donated it to the Field Museum. Lots of it got to the in scientific laboratories for study within a short time. Totally, we have about 39 kilograms of Murchison at the Field Museum, together with other specimens, about 13,000 specimens from 1,700 distinct meteorite falls. And it's about the 5th or 6th largest collection worldwide and the largest collection at a private research institution. And we take good care of those meteorites. You can see every single piece is in a box with a label. We have a database where we track everything. And then most pieces of Murchison are actually in desiccated cabinets. These have silica gel that takes out the water out of the air so they don't get altered. And we make sure that lots of Murchison is available today for the scientific community, but also for many more generations of scientists. So, but people all over the world can submit requests to us for studying Murchison and other meteorites, and we evaluate them very critically, and then usually send a sample. So not normally we don't need to send large rocks to them. Most sample requests are on the order of milligrams or even less. But, and I mentioned Murchison is a very special meteorite. Because it was collected so quickly after the fall, it was made available to science, and because so much material fell and was recovered. Only 4% of all the meteorites that fall today are Carbonaceouschondrites. Murchison is one of them. It is the biggest of its type, the so-called CM2 chondrites. 100 kilograms fell, and that was at the time when it fell, 1969, and still today, 2019. There was one fall, we heard about it yesterday, this year, in April in Costa Rica, which is also a CM2 chondrite, but it's only a little bit less than 30 kilos. So Murchison is still the record holder in this category. Just to remind everyone, we are in Murchison on planet Earth, and planet Earth is orbiting the sun orbiting the sun, and the sun orbits the galactic center. This is the galactic center. This is an artistic representation of the Milky Way galaxy, together with about 250 billion other stars, and one orbit takes about 220 million years. So Murchison experienced experienced about 20 orbits around the galactic center. Murchison is 4.6 billion years old, and I think it formed from a cloud of gas and dust 4.6 billion years ago, long before the planets formed. Take this artistic representation of the early solar system. This is a mix of gas and dust, and imagine you take a piece out of this gas and dust and condense it, basically smash it together into rock, and this is what you get. It's essentially Murchison, a sedimentary rock from the early solar system. We will hear later this afternoon and tomorrow about the different components in Murchison, the white components, the dark matrix, and so on. And what I will talk to you about now is a small fraction of Murchison that's found in the fine-grained matrix, which is even older than Murchison itself. It's pre-solar material, which is older than our solar system, that has been discovered in Murchison and also other Carbonaceouschondrites in 1987. And we can analyze now this pre-solar material, learn something about the time before the sun and planets even existed. Before I start talking about that, just talk about where Murchison comes from. I think Murchison comes from a carbonaceous asteroid, a minor planet that orbited the sun. Many of those minor planets, these asteroids, orbit the sun between Mars and Jupiter. And this is actually a picture taken by the Japanese Hayabusa 2 spacecraft of an asteroid, of a carbonaceous asteroid called Ryugu. It's about 1 kilometer in diameter. And there were some rovers dropped from the spacecraft onto the surface and took close-up images of the surface of Ryugu. And it looks remarkably similar to Murchison. You see the dark matrix with the white objects. Look at the scale bar, it's 5 centimeters here. This was a report in August by the team from the Hayabusa mission, but just wanted to show you this. When I saw that, I thought that was really striking. And we are not saying that Murchison comes from Ryugu, but from a similar objects, possibly. Yeah, another close-up from Ryugu. And back to Murchison. This is one of the largest pieces we have at the museum that's also on public display. This is actually the piece that you saw previously. One of the finders had it in his hand from the Gillick family. And this is a close-up of the interior. So look at the difference. The smooth fusion crust here. Here the fusion crust is missing. The fusion crust forms obviously when the meteorite flies through the atmosphere. And here you can see again the interior with the the white inclusions, chondrules, the round spherules, and the dark matrix. And we will focus on the dark matrix, which contains organic molecules. When I talk about organics, I don't mean it's formed by life. It's just molecules that we also find in life. These, in Murchison, organic geochemists found amino acids, which are considered as the building blocks of life. They found sugar-related compounds, alcohols, kerogens, and so on. So it's essentially a whole mix, a whole zoo of organic molecules that came to Earth, and we think many of those compounds are found on Earth. They're also found in living organisms, but that doesn't mean life came from space. It just means those building blocks for life could have likely been delivered by objects like Murchison in the early solar system. And analyzing the chemistry of those different compounds, organic cosmochemists and geochemists think that some of them formed in interstellar space before, in pre-solar time, before the solar system formed. Some of them formed in the early solar system and in the parent body of Murchison. So there are all kinds of, a mix of different origins, but that came to Earth in 1969, but also throughout Earth's history, Carbonaceouschondrites fell to Earth. And in the beginning, when Earth formed, there was much more material coming to Earth, and we think Carbonaceouschondrites could have played an important role in bringing the building blocks for life. It's still a long way then to get life from these simpler compounds compared to the more complex compounds that we find in living organisms. That's one group of interesting compounds that are found in meteorite, in the Murchison meteorite, and some of them are pre-solar. Another interesting group are inorganic materials, like pre-solar grains, and I'll talk about this now. This is actually the topic I work on most, and that is that I'm very interested in. And these pre-solar minerals are only a tiny fraction of what is actually found in meteorite. They're only parts per million. So if you have 1,000,000 grains, if you make a powder out of Murchison, you have to look at 1,000,000 different mineral grains to find one pre-solar one. So it's a tiny component. And to find it, it takes a lot of time to do that. So it's like finding a needle in a haystack. And a group by Professor Anders at the University of Chicago developed a method to find that needle more quickly, not looking at every single mineral, but by burning down the haystack to find a needle. We cannot just burn Murchison, but we can first crush Murchison a little gently, and then we get something like this. This is a petri dish, a glass dish, with sand extracted from Murchison. It's not quartz, but it's olivine, hibonite, all kinds of different minerals and matrix. And then we can throw that into a heavy liquid. This is like oil, but denser. So the lighter minerals float to the surface. We can just scoop them off the surface. And the heavier stuff sinks to the bottom. So we can already separate some of the components. And the next step is we use acids. We put them in centrifuge tubes to dissolve away everything we think that's from the solar system. After, of course, we picked interesting samples out. And then we get to that. This cube here has 1,000,000 little cubes. And I highlighted the pre-solar fraction, which is the 1,000,000th of that whole cube. After burning down the haystack, we find a needle. And essentially, this is for the Allende meteorite, which is also fell in 1969. Process Murchison the same way, treated in acids, and at the end get a little acid residue. And the first type of pre-solar mineral that was discovered is diamond. And this is a vial with diamond. So this is the acid residue at the bottom of this vial. Swims in, essentially, is suspended in alcohol-water mixture. And I have a piece here. I will hand this around, and I'd just like to get it back. So at the end of my talk, this is a vial with nanodiamonds that was extracted from the Allende meteorite. The reason why we didn't do that from Murchison is that Allende has a little bit more of those, but Murchison has more of the silicon carbide minerals. The silicon carbide minerals was the second phase that was discovered, and this is a electron microscope image of a pre-solar silicon carbide. So this this white bar here is 2/1,000,000th of a meter, so it's or 2,000ths of a millimeter. Really small grains. You cannot see them with the naked eye. But you have to use you can use a high-powered microscope or electron microscope. And here is a gallery of silicon carbide grains that we extracted from Murchison. And Murchison, actually, the meteorite I started working first. I mentioned that before. And we looked at these, the compositions of those silicon carbide minerals. Silicon carbide is very common on Earth in lab, where people use it to polish, it's in sandpaper, to polish rocks and so on and other materials. So we have to be very careful not to contaminate our lab with sandpaper. You would find silicon carbide everywhere. So we do that in a clean lab. And why is it called Presolar? I already mentioned it formed before the solar system, but it is contained in the rock, in Murchison and other carbonaceous chondrites. The rock itself can be dated. It's 4.6 billion years old. These minerals have compositions that are different from anything in the solar system. And so they couldn't have formed in the solar system. And because they're in a rock that's older than the planets and as old as the solar system, they must have formed before the solar system. And where do they come from? We can look at the composition, and we look, for example, in this image, I promise you this is the most technical plot I show you. It's very simple. We have silicon carbide is silicon and carbon, and two elements. It's a very simple mineral. And carbon has two different forms, two different varieties. One is a little bit heavier than the other one. It's carbon-12. This is the carbon that we are made out of mainly. And 1% of the carbon has one neutron more. It's a little bit heavier. It's carbon-13. And everything on Earth has a carbon-12 to 13 ratio of 89. So it would be here. If you take the presolar grains, you have a huge variety of different carbon varieties in it. So you have silicon carbide grains which have 50-50 of carbon-12 to 13. Then you have those which have almost no carbon-13. So you have the whole range. And this is just a histogram. You can see here you have about 400 grains with this composition, 250 grains with this composition, and so on. And this composition of these grains, of these presolar grains from Murchison, they seem to perfectly match the composition of so-called carbon stars. And this is an astronomical photograph of a carbon star. The carbon stars are sun-like stars at the end of their life, where they shed their outer layers. Their outer layers become cool down, and they also include carbon that is synthesized in the star, that is formed in the star by nuclear reactions at the end, at the final stages of the star. And then you have a gas around the star, a cloud essentially, where dust starts to form. You have essentially looks like smoke. It's carbonaceous dust. You form silicon carbide, you form graphite, and astronomers can measure the composition of that gas, and it matches the composition of the grains we get out of Murchison. We can do that exercise for different elements and come up always with a good match, and that basically tells us or lets us believe that these presolar silicon carbide grains from Murchison, most of them come from these type of stars, from carbon stars. We can do that for a large number of grains, and we find different types of stars match the composition. So carbon stars are essentially 90% of all the grains come from these carbon stars, and 1% comes from more massive stars, but I don't go into these details. What I want to show you is the mix of presolar grains that we find in meteorites like Murchison. It doesn't come from one type of star or one star, but it comes from hundreds or more stars. Each dot that you see on that diagram here, this is nitrogen, the nitrogen composition and the carbon composition, could come from a different star. And this is the starting material from which we formed. Essentially, the carbon in your body formed in carbon stars. And they only did these basically the atoms in your body, the carbon atoms in your body, and the carbon atoms in the diamonds that you see in the vial that's going around could have the same source, could have the same stellar source. The difference is that the carbon atoms in these stardust grains from Murchison haven't changed since haven't changed their. They're still part of. They're still in the mineral in which they formed. So basically, the carbon forms in the star, gets ejected outside of the star, it condenses into a mineral and doesn't change anymore for more than 4.6 billion years. In our body, we might have, the carbon comes from maybe from the same stars, but it has gone through many different stages of evolution, but it has the same origin. So we are essentially all made out of stardust, just a different one. What you see, hold in your hand today, is the original, basically how the carbon originally started in its journey in a star, and is preserved till the present day. And that's why Murchison is so important, because it preserves the original composition from the starting material from which we, the Earth and life on Earth formed. So briefly, this is a cartoon I show here. This is actually a Hubble Space Telescope photograph of a planetary nebula. That's an end product of a solar-like star where it ejects its outer layers. They can have different shapes. They're really beautiful, can be observed in the night sky even with an amateur telescope. And in this planetary nebula, you form these dust grains, stardust grains, and they start their journey through space. And here's another example of a planetary nebula where you form large dust grains. Here you have dust grains that form up, that are thought to have several millimeters in diameter. So these ones you could even see, but they're rare. Typically they're smaller. And we can measure, we can determine the journey, how long they fly through space. They start, oops, that was wrong button. They start their journey in the outflows of such a star, fly through space, and while they are in space, they are exposed to cosmic rays. Cosmic rays are high energy particles that come from all directions and go through these particles, go through these dust grains and form new gas, new elements within the mineral, and they accumulate. And the longer these particles fly through space, the more radiations they get, the more elements form. It's similar if you have if rain is going on outside, you put an empty bucket of outside, it fills up with water. The longer you have it outside, the more water you will have, assuming the rain is always constant. And this is essentially the same method that we use. Instead of rain, we use cosmic rays and products of cosmic rays, and then we count the atoms that are produced through this exposure. It's like counting the raindrops. And by the number, the number of atoms tells us how many million years those mineral grains were exposed to cosmic rays. It's a very simple concept. To count the atoms, a little bit more complicated, but we simply use a mass spectrometer instead of a scale or a bucket. But the principle is the same. Gets a little bit exposure from the early sun, which was also active, and then once the tiny mineral grain becomes part of the Murchison parent body, the clock stops ticking, because inside the Murchison parent body, it is protected from cosmic rays. And then we can actually calculate how long they were exposed, and we find, so far we have done that for about 50 grains, and we found that the majority was flying through space for about 300 million years or less. That means the sun and the solar system is 4.6 billion years old. You add 300 million, and you get to about 5 billion years, so they're about 5 billion years old. And then a small minority is older than 1 billion years than the sun, which makes them about 5.5, 6 billion years. The oldest one that we found is about 7 billion years with a large error. But I always say having an age with a large error is better than having no age. So anyway, we can then, I don't want to go into this is too complicated. I don't have time to go into that, otherwise I would have loved to explain it to you. Maybe we have time in the questions, but what I want to end with is this timeline of natural history. This is today, 0. We go back in time, this is billions of years, and the start of the solar system is 4.6 billion years, and this is what initially was accessible to the study of meteorites. the universe itself is 13.7 billion years old, so only a small fraction. And thanks to Murchison and other Carbonaceouschondrites, we can extend this time period in natural history to about almost 7 billion years that is accessible through the study of meteorites. Everything older can be observed astronomically only. And obviously, everything in the future is just predictions. But in order to understand our future, what will happen in the future, we have to see and better understand what happened in the past. And thanks to Murchison, we know a lot more about this time period here at the end of this timeline. Put this in perspective, if the whole universe, 13.7 billion years, is one terrestrial year, 365 days, the start of the solar system is about 120 days, about 4 months, and we can extend that back in time thanks to Murchison for a few months. And to finish up, I want to show you this slide, which is the whole process from the formation of dust and carbon and many other elements in stars, in the element factories, the journey through space, through our galaxy, through the solar system, until meteorites land on Earth. It's all captured in Murchison. Thank you very much.
Thank you, Philip. That was absolutely stunning. We've got a few minutes to take some questions. If there's some questions from the audience, I think that there might be a few. John?
If we've got a few minutes, can we look at the slide we asked?
Yeah, I can do that very quickly. Yes, okay. So you have to I will point out, it's a very busy diagram. That's why I wanted to skip it over. I realized I was running out of time, but since you asked the question, that's fine. This is the pre-solar time before present. Here, zero formation of the sun. Here, on this axis is actually time before present. Formation of the solar system, 4.6 billion years, and so on, going back in time. The blue mountains that you see here, that's essentially just the ages of pre-solar grains. So you see they're higher here because most grains have ages that are 300 million years or less before the sun, which makes them about 5 billion years old. And then only a few grains have older ages. And what I plotted here, this green line, the purple line, and the red line, I wanted to see, okay, what happened in our galaxy in the past based on astronomical observations. Astronomers think that about 7 to 9 billion years ago, there was a bump in star formation. So there was a process, we don't know what happened, but there were more stars than normal forming. And these stars, we think, are the parent stars of us and the pre-solar grains. Stars don't produce dust at the beginning or during their life. They produce dust at the end of their life. So these stars form here, 7 to 9 billion years ago. They age, and at the end of their life, they produce this dust. And if we would have a flat star formation, if there wouldn't be this bump in star formation, we couldn't explain that there is so many young grains. You expect more younger grains than older ones because the older ones get destroyed to collisions, but not that many more. So this bump in star formation in our galaxy explains the bump in many more young ages than we would otherwise expect.
Thank you. Very good. Any other questions? Yes, Paul.
What caused the bump?
That's a question. That's not clear. There are different hypotheses. One hypothesis says there were cold streams of cold gas streaming onto the disk of our galaxy, bringing on new matter that could have triggered star formation. But that's just one of several explanations. Yes, down the back there.
What causes the change between carbon-13 and carbon-12 in space? What's the
So the question was, why do we have sometimes more and sometimes less carbon-12 versus 13? So what happens is, in these stars, like this red giant, you have processes going on in the center of the star, in the inner part of the star, that produce carbon. And so, for example, you have helium atoms. The helium is basically the end product of the main stage of a star's life. At the end of a star's life, this helium gets fused together to form carbon. You also have other processes that are going on that produce neutrons and that add to basically the existing nuclei, so you form heavier isotopes. So this is basically I would say, you have many different reactions going on in these stars, and depending on the mass and the composition of the star, the different reactions matter more or less, and that's why you get different outputs.
Okay, thank you. Yes?
In 1969, another Carbonaceouschondrite was found called Allende. Can you tell me what the differences between the two are there?
No, that's it. The question was, how does Allende compare to Murchison? Both were Carbonaceouschondrites. Allende fell in the first half of the year before Murchison, and that fell in Mexico. It's about 10 times more material fell during the Allende fall, but Allende is a different type of carbonaceous chondrite. It is, the components in Allende are more altered. For example, the first condensates that formed in the solar system, that's the topic Trevor Island will talk about next, I guess. They are more altered in Allende than in Murchison. So Murchison is the more pristine one of the two. They're not coming, they're very likely not coming from the same parent body.
I'll take a couple more questions because Philip has got such fantastic material. David?
Anyway, I'd just like to get your answer on this. We talked about this earlier. The material, the molecular cloud, the pre-proto-SIMS sort of material is made that up. Are we finding the same sort of constituents in maybe the Andromeda galaxy or other galaxies like that? Or how common do you think those elements are in the interstellar medium?
So if I understand your question correctly, you're asking how unique is the solar system compared to others. I mean, astronomers observe star formation going on in our own galaxy. There is lots of star formation regions. And the starting materials of these different stars can vary, and they can have different starting compositions. And what I didn't mention, I should mention now, is that our sun started from material that was already produced in stars before. And those stars that produced that material, those parent stars of us and the presolar grains, they are not first generation stars. They already inherited material from previous generations of stars. And there is heterogeneity in our galaxy. That means the composition vary of different, and then in other galaxies, you have again different compositions, like the Magellanic clouds, they have different compositions than our galaxy.
Would it be too arrogant to say that medium, that molecular structure that we have, that forms us, that would be fairly widespread? Is that too arrogant?
It's very similar. It's very similar, but there are differences in the composition. But the processes are the same.
Sounds like recycling, doesn't it, Bill?
Yes.
I just have one question. The presolar grains, we saw that fantastic slide of the spiral of the entire galaxy and where we are in it.
Yeah.
How far travelled would those grains be? Were they near neighbour stars on that entire spiral? Where do they come from in the galaxy that got incorporated into our system?
That's completely unknown. We just know that they have been out there for a long time. The youngest ones, they have only done one orbit around the galactic center. It takes them about 200 million years, or some of them even less. They have maybe done half an orbit, and others have done several. But we don't know if they traveled in the galactic latitude or how they traveled. We have no idea. We just know we just think we know how old they are. But there are, of course, also uncertainties in these ages. If they traveled close to a very active star, this star could have produced more of those raindrops, cosmogenic nuclides, and they appear older than they are. So there are still many unknowns, and we're, I guess, just scratching the surface of our knowledge about the pre-solar history of our galaxy.
Thanks very much. Philipp Heck, brilliant talk. Thank you very much.
Thank you.